Right now, at this exact moment, there is a place in the Indian Ocean where the ocean surface sits 348 feet lower than everywhere else around it. Not because of a storm, not because of a current, because gravity there is weaker. Something deep beneath the seafloor is missing, some enormous amount of mass that should be there and simply is not. And the ocean is literally sinking into that absence. This anomaly is almost the size of India itself. It has been sitting there for at least 20 million years. It was discovered in 1948, and for 75 years, nobody could explain it. That just changed. And the answer is stranger than anything scientists expected. Let's start with scale, because this thing is almost impossible to visualize. The Indian Ocean Geoid Low, that's its official name, covers roughly 1.2 million square miles. To put that in perspective, the entire island of Manhattan is about 23 square miles. You could fit Manhattan inside this anomaly around 50,000 times. The entire country of India covers about 1.3 million square miles. This gravity hole is almost that big. And what it does to the ocean above it is genuinely surreal. If you removed all the tides and currents from the Indian Ocean and let the water settle purely based on gravity, the way it would if the Earth were completely still, the surface of the water directly above this anomaly would sit 106 meters, or 348 feet, lower than the water everywhere else around it. That's a hole in the ocean. Not a physical hole you could sail into, the water fills it. But the ocean's surface is not flat. It bulges and dips based on where gravity is stronger and weaker. And this is the biggest dip on the entire planet. It sits just southwest of Sri Lanka, south of the tip of India. Ships have been sailing over it for centuries. You cannot feel it. You cannot see it. But it is there, and it is the most extreme gravitational anomaly anywhere on Earth. The story of how we discovered this thing is almost as interesting as the thing itself. In 1948, a Dutch geophysicist named Felix Venning Mynes was doing a routine gravity survey from a ship in the Indian Ocean. He was measuring tiny fluctuations in gravitational pull using instruments on board, and he noticed something wrong. The readings in one large region were consistently, significantly weaker than they should have been. He logged it. Scientists noted it. And for decades it sat in the literature as an unexplained curiosity. The real picture only came into focus when we got satellites. GPS and orbital gravity missions, particularly NASA's GRACE program, which stands for Gravity Recovery and Climate Experiment, allowed scientists to build a full global map of gravitational variation across the entire planet. And what showed up in the Indian Ocean was dramatic. A massive circular depression in the geoid, the technical term for the gravity-defined shape of the Earth, sitting right where Venning Mynes had flagged his strange readings 50 years earlier. The geoid, by the way, is not the physical ocean floor. It is an imaginary surface that describes where sea level would be if the ocean were perfectly still and shaped entirely by gravity. On a perfectly uniform planet, it would be a smooth sphere. On the real Earth, it looks like a lumpy, dented ball, and the deepest dent of all is right there, south of India. Gravity there is 0.085% weaker than the global average. That sounds tiny, but applied across 1.2 million square miles of ocean, it is enough to pull the sea surface down by over 100 meters. The numbers are real. The instruments confirmed them independently multiple times. This is not a measurement error. Here is what made this so frustrating for so long. Earth's gravity varies for a fairly simple reason in most places. Denser material pulls harder. Less dense material pulls less. A mountain range has more mass, so gravity is slightly stronger above it. A deep ocean trench has less rock and more water, so gravity is slightly weaker. These variations are predictable and well understood. But the Indian Ocean anomaly didn't fit any of the standard explanations. The seafloor there is ordinary. The crust thickness is roughly normal. There is no obvious missing mountain, no gaping trench. Whatever was causing the weakness in gravity was not sitting on the surface. It was somewhere far, far deeper, and for a long time, scientists had no tools capable of seeing that deep. Several theories circulated over the decades. Maybe it was related to the subduction of an ancient tectonic plate. Maybe it was a remnant of some prehistoric geological event. Maybe the mantle structure in that region was unusually thin. None of the models quite worked. None of them fully reproduced the anomaly's size, depth, and location using only the physical evidence available. Then in 2023, a team of researchers from the Indian Institute of Science in Bangalore, led by Professor Atreyi Ghosh, published a study in Geophysical Research Letters that finally cracked it. And the answer required going back not 20 million years, not 100 million years, but 200 million years, to an ocean that no longer exists. This is the part that still feels almost too strange to be real. 200 million years ago, Earth's land masses were arranged completely differently. There were two giant supercontinents, Laurasia in the north and Gondwana in the south, and between them sat an ocean called the Tethys. It was enormous, warm, shallow in some places, deep in others, teeming with life. And then, very slowly, it began to disappear. As the Indian subcontinent broke away from Gondwana and began its long drift northward, eventually colliding with Asia to form the Himalayas, it passed over the floor of the ancient Tethys Ocean. And as it moved, it pushed that seafloor down. The old oceanic crust of the Tethys, massive slabs of it, was shoved under the Indian plate and began sinking into the mantle. Geologists call this subduction. But here is where it gets unusual. As those ancient Tethian slabs sank deeper into the lower mantle beneath what is now the region around East Africa, they disturbed something else, a massive zone of hot, slow-moving rock beneath Africa known as the African Large Low Shear Velocity Province. Scientists call it, simply, the African Blob. That disturbance caused columns of hot, low-density material to rise upward from the African blob, mantle plumes, spreading beneath the Indian Ocean. Hot rock is less dense than cold rock. Less dense material means less mass. Less mass means weaker gravity. And weaker gravity means the ocean surface above it sinks. The gravity hole in the Indian Ocean is the ghost of a dead ocean, filtered through 200 million years of geological chain reactions, expressed as a dent in the sea surface that you could fit India inside. That is what is sitting beneath the Indian Ocean right now. The reason this matters goes beyond one anomaly in one ocean. The GRACE satellite mission and its successor, GRACE-FO, have now built the most detailed global gravity map ever produced. And what that map shows is that the Indian Ocean anomaly is the most extreme example of something that is everywhere. The surface of this planet is not uniform. Gravity varies across every ocean, every continent, every mountain range. The Earth is not a smooth sphere. It is a lumpy, uneven object whose shape is constantly, if slowly, changing. Those mantle plumes beneath the Indian Ocean are still moving. The African blob is still there. The question of whether the anomaly will persist, grow, shrink, or shift over the next tens of millions of years depends on how those deep structures evolve. And Professor Ghosh has been direct that the models cannot predict that with certainty yet. What scientists do know is that the tools for understanding this have improved enormously. Seismic tomography, which uses earthquake waves passing through the Earth to build 3D images of the interior, the same way a medical CT scan uses X-rays to image a body, has confirmed the presence of the low-density material beneath the Indian Ocean down to depths of nearly 900 kilometers. That is more than 25 times deeper than the deepest point of the Mariana Trench. We are imaging the inside of a planet using the ripples from earthquakes, detecting the ghost of an ocean that vanished 200 million years ago, reading its influence in the shape of the sea surface today. The chain of inference that connects all of that is one of the genuine achievements of modern geoscience, and almost nobody has heard of it. There is one more thing worth sitting with. The deepest any drill has ever reached into the Earth is about 12 kilometers. The Kola Super Deep borehole in Russia, which took 24 years to drill and was finally abandoned in 1992 when the rock simply got too hot and started closing around the drill. The mantle plumes responsible for the Indian Ocean anomaly begin at 300 kilometers down. We have never physically touched anything that deep. Everything we know about what is happening down there comes from indirect measurement. Gravity sensors, seismic waves, satellite altimetry. We are reading the deep earth the way a doctor reads a heartbeat through a stethoscope. From the outside, in the dark, the Indian Ocean. Geoid Low has been sitting there since before humans existed. Ships have crossed it for thousands of years without knowing. The ancient Tethys Ocean that caused it has been gone for 200 million years. And we only worked out the connection in 2023. That gap between something this large and this consequential existing, and us understanding why, is a useful reminder of how much is still happening beneath this planet that we have not figured out yet. The crust we live on is 35 kilometers thick. Everything below that is inference, model, and educated guess built on centuries of careful observation. The gravity hole in the Indian Ocean is not a threat. It is not growing fast enough to matter on any human timescale, but it is real, it is enormous, and it is the clearest window we have into the deep machinery of a planet that is far stranger and far more active than it looks from the surface. If you want to go further down into what happens the day we find something even bigger than this, check out the next video. We take everything we just covered and ask one question. What if we found a void large enough to swallow Manhattan whole? And what would it mean for the ground we are standing on?